Okay, so last time we built transformers by stacking different transformer blocks on top of each other. And just to remind ourselves, the input, you get a sequence of discrete tokens, and it gets projected to a smaller dimension through an embedding matrix, and it gets inserted into stacks of transformer blocks. And as you pass through all the blocks, final layer, you up project them so that it matches the dictionary size. So you get batch size, sequence length, times number of words in the vocabulary, and we interpret them as unnormalized probabilities predicting the next tokens. And then we implemented cross entropy loss, so we can measure the correctness of the output. Today, we'll keep building, and we'll cover the backpropagation for the transformer and also different optimizers. Okay, so I think the lecture 9 material is uploaded on ETL. Okay. So I think there are two files there. So open up 9.1 first. Okay, so let's revisit the transformer block. And you now have a set of to-dos here. So let's see. We have already provided some useful tools for you in the models file. And we're going to create some random inputs. So batch size, sequence length, vocabulary size, number of layers, number of heads, and head dimension, and create some random tokens from the vocabulary. And H is some random embedding. And this is your rope cosines and sines. Okay, so in the constructor, we set all the variables and self-dead attention, feed forward, and respective norms. And this is what we covered last time. So if you still remember, let's just go back to the equation. Lecture 9. Okay. This was the routings. So input X comes in, normalize, attention, add X again, that's H. Gets passed through RMS norm again, feed forward, plus H, that's output. Now we're going to do this in reverse for the backprop. Right? X comes in here, and attention norm, apply your attention, you add X, that's H, and RMS norm again, feed forward, add H again, that's output. That's what happens inside one transformer block. Okay, now we're going to implement the backward for the transformer block. So for each submodule that we provided, these guys, you can just call backward to compute the backward for the respective blocks, well, submodules. And the output should be grad output. So, sorry, that's the input. This is the upstream gradient, dl dy, in the lecture. This is dl dx, gradient of the loss with respect to input to the transformer block. These are not really necessary, but we do it just to check the implementation in the test. So once you finish implementing, then we have provided different tests to numerically check whether your implementation is correct. And once you're done, yeah, let's just do this check first. So implement these lines, and you should see all the green check marks. So just remember, now for the forward, input came in here in X here, and this was output. Now your dl dy is coming in from here, and you need to have something that come out here, right? Just make sure to be super careful what the residual connections here and here. All right, let's do this. All done? Anyone finished? Still working? Anyone finished? Oh, okay. Did you pass all the tests? No? Okay. Let's look at it together. So okay. So it was composed of two parts, one for the attention, one for the feed forward. Input is going to, DLDY is going to come flowing in here. So let's take care of this feed forward first. Okay, it has two paths. How about this path? Okay, so the order was RMS norm, feed forward. So it's going to be in reverse. So we're going to do feed forward dot backward first. And then we're going to do RMS norm dot backward. And for this path here, we're going to add self. Right? It's just addition, so it's an identity operation for backprop. Where in terms of flow, it just flows both ways. One way here, another way here, this way, feed forward, and then FFT and RMS norm. Okay, let's name the output of this whole thing. Grad H. That's gonna represent DLD. I don't know, DLDZ, which is in between attention and FFN norm. Sorry, the feed forward. Okay, so now we have this DLDZ here. It's come in and flow here and here. In the forward, the order was attention norm, which was RMS norm, and then attention. So now we're going to do it backwards. So call attention.backward on DLDZ. It's going to give you all three of them. Strictly, these are not really necessary for backprop, but this is just to check. That's one path taken care of, this path here. How about this path? We just add in DLDZ again, this guy here, and that's the output. That's now DLDX. All right. Sometimes it can fail, but just run it again. We set the sensitivity very, very sensitive. Let's see. Okay. Sometimes, yeah, it can fail, but not because the implementation is wrong, but because this is doing, let me see if I can write somewhere. doing this numerical gradient checking for every dimension. So every dimension I, it's perturbing forward, backward, and basically computing numerical gradient. So we are checking whatever you compute with your Python against a vector here. And if the L2 norm difference between these two guys are less than some number, some tolerance, we output some green check. And sometimes it's not happy. Sometimes it will pass our test. Okay, anyways, it was easy. So for the forward, you take this path. For the backward, input comes in here, output comes in here. You just need to do everything in reverse. And let's see. Now, another remaining thing is cross-entropy loss. So we implemented the forward for the cross-entropy loss last time. And we used the gather operation in PyTorch to select the target for the logic targets. And now for the backward, this used to be your to-do previously, but we decided to just give you the solution. All right, so now we have everything, right? Okay, now let's do the backward for the entire module. So transformer, we looked at this last time. So input comes in, and you convert everything with an embedding matrix, and initializer defines all the necessary other things like rope, normalizer, linear cross-entropy loss. And for the forward, you first do embedding projection and create a mask for causal mask, and define a list of layers which correspond to different blocks, transformer blocks. And you normalize output and multiply by the output matrix to convert the hidden dimension to the logic dimension, so we can interpret it as unnormalized logic probabilities and apply softmax loss. For the backward, now it's your turn to implement. So is this reliant on the previous implementation? Attention, feed forward. Transformer block. Transformer block is not imported. So yeah, I'll just give you 1 minute to copy paste the solution for the transformer block because it's reliant on it. Yeah, so copy paste this into transformer block implementation in case you haven't finished. Now we're going to chain this together and create a full transformer and implement the backward. And it's going to be straightforward now, right? So there's no digital connection inside. Otherwise, I mean, the digital connection is only inside the transformer block, but outside you don't need to worry about anything. You just need to reverse the forward process, right? Backward the loss, call the backward for each transformer block, and pretty much done, right? All done. Everybody copied the solution. Need more time? All right, so okay. Transformer block we just finished. Gradient of the loss is given to you, and this is the entire transformer. For process I already explained. Now it's your turn to implement the backward. So remember to use the backward method for each submodule. And what are the input parameters? Grad logits. So this is gradient of the logit of shape, batch size, sequence length, vocabulary size, grad loss. This is typically set to 1. So this is to make correspondence to the lecture DL with respect to DL. So it's typically initialized to 1. Okay, so here, if you look at the for process, where is the beginning and ending? This is beginning, computing the embedding, and if label is not given, if the label is given, it computes the logit and the loss. If the label is not given, then it outputs the logit itself. Stops there, because it cannot compute the loss without without the labels. So if you look at this for loop, it repeats the layer indices in reverse order automatically, and you just need to compute DLDX based on DLDY by multiplying the local gradient, pass it as the input to the previous transformer block, and that's it. finished? Need some more time. Okay, anyone finished? Okay, all right. So the backward portion. So if the gradient loss is provided, then you take this loss function and execute backward on the input, and it's going to give you logits and labels. And for the grad logits, you add it to the provided grad logits. Most of the times, this is going to be initialized to 0 from outside. And then we just need to go in reverse. So this output H, you have this H, and it was multiplied with output matrix. Now we need to do backward on the output matrix, right? Okay, now it flows through here, and it entered the normalization. So we need to call norm the backward. So now we are at here, this point. Okay, we came in all the way to here. Now we need to, in reverse, wire through the transformer blocks in reverse order. Okay, in reverse order, get the layer, execute the backward on grad H. It's the output, gets fed back into the previous layer, and repeats for how many n layers. Okay, what else? Now we are at here, at this point. Here, this embed is matrix multiply, and we're going to call backward on embed, and the result of that is the output that we want. Okay, so let's see what it's testing. So it's testing the gradients for everything, and everything includes weights for the embedding layer. For the layer 0, it's testing WQ, so query, key, value, output matrices, weights, and bias. And it's also testing the feed-forward layer, the sweet glue portion, weights and biases. And layer 1, so this layer corresponds to transformer block index. Repeats the same thing for the next transformer block. And output matrix also has weights and bias. And that's all what it's testing. Okay, so let's see. Let's open up the second. Core lab. So we're going to come back to this in the lecture. So I believe in the lecture we haven't really discussed different optimizers. But while we are at it, we're gonna cover this first because we want this experience to be consecutive and fully cover transformers sort of end to end. So in order to do that, we need to define optimizers and actually train the models that we just built. Okay, so while it's executing, I just wanted to give you some, so we're going to come back to this later, but I just wanted to give you some intuition. So why does transformer work so well compared to other network architectures? So say you have input sequence, I am such a student. All of this is stored in the memory. So we convert this into query and value and key embedding, and this now resides in the memory. And in order to compute what's going to follow, okay, now it needs to generate logics for the token that follows this entire sequence. In order to do this, it should be K. In order to generate this token, what's the underlying computation? We take the outer product of the query and key. So we take this guy, this whole thing outer product it, build the attention map, and this attention map now is of size entire sequence length. We take this guy and multiply the value matrix to produce an output. So what's happening is every single token in the memory is communicating with each other to generate this single next token. So this may not sound very complicated or exciting, but so this is just because the input sequence is very short now for this example. So in practice, this input sequence is very, very long. It's about, it can support the modern architectures like QN 3.5 can support up to, I think something like 150K tokens. 15만 sequence length. So we can insert a very large information into it, and we can insert, I don't know, thousands of pages of PDF and Wikipedia articles and everything. So it's stored in the memory, and in order to generate a single token, it attends to a vast history. Some of them may be relevant to generate this, some of them may not be relevant. That's encoded in the attention map. And this capability to explicitly reference all previous tokens, it's very, very powerful. It becomes more and more powerful, especially if the context length, the sequence becomes very large. That's where the power comes in. It also has downsides because obviously there's a limit. Where is the limit coming from? Can I insert, I don't know, billion tokens here? What's going to happen? Right, hardware cannot support. To be specifically, which hardware? Right. So specifically, there's a memory problem. So peak memory is basically how much information you can store in the computer So there's CPU memory and GPU memory, which is typically HBM. And as we insert more and more tokens, the peak memory becomes too large, so we eventually hit out of memory error. So how do we deal with this? So in, I think, 2 lectures, we're going to talk about pre-filling and decoding. That's a very basic way to do this. And there's also a lineup technique called KB cache compression. So eventually, these cache of the values, query and key, that's the bottleneck. So how do we compress this knowledge? So it may be possible that we do not need to actually store all the token information. That's one way, and the other is obviously quantization. So maybe we do not need to store information in floating point 16. Maybe it will still work if we do floating point 4 bits. So this is a very active research area. And I heard, okay, so Google presented this paper called TurboQuant, and it was related to compressing the KB cache and quantization. And there was a reaction from the stock market leading to sharp drop in the stock prices for the memory companies. But I think it was just an overreaction from the market. Because if we can push down the memory, it's a good thing because we can enlarge the context length. Now the context length is limited to 150K tokens. So if we can limit the memory here, reduce the memory here, we can, I don't know, support like, I don't know, 1 million tokens or something. It enables something that was impossible before. So now it's not a bad news for memory companies, in my point of view. All right. Just intuition and where it's going. All right, so let's pick up from 9.2 optimizer. So in the lecture, we discussed stochastic gradient descent, right? And in practice, it's never used, unfortunately. And we need to introduce a lot more technical. Some people call it black magic. Some people call it hacks. Some people call it practical modifications to the optimizer. So we're going to introduce an optimizer class and derive from it and implement some changes to it. So we're going to introduce the vanilla SGD, and it updates. So the structure in the code is we have this base class optimizer, and you need to implement this update dict. So this is how much update you want to apply to the parameters. And we have SGD, you need to implement update dict, and we have momentum, implement this update dict, RMS prop, and atom optimizer, and that's how it's structured. So let's look at the abstract base class first. The base class first. So, okay, let's read this through. So this gives you the list of parameters in the model. And this is the weight decay, or the L2 regularizer for the parameters to prevent overfitting. And step, this is basically where the gradient update happens. So you have your parameter, and you're going to subtract step dict, which is coming from the update dict. So this update dict is supposed to give you the update amount that you're going to apply, and this is going to take away that update amount. So this is basically learning rate times the gradient. And it also does gradient norm. So this is obvious if you look at the equation here. So if you apply gradient to the right hand side here, that's the gradient of the loss plus gamma times the theta, right? Right? So this part is for gradient of this guy, the loss. The second part is for this part. If you take the gradient with respect to theta here, 1 over 2 and 2, they vanish. So this becomes gamma times theta. So that's just adding the parameter. All right. So WD gradient, that's just so yeah, this part not very important, but this is basically entire gradient update, and this portion is for, well, basically same thing. This is just taking the norm of this whole part, and this part is for the regularizer gradient, which is gamma times the parameter. Gamma WD is given here as a default parameter, and we're not going to change it. This is just going to set to 0.0001. So what I want to say is, in our implementation practice, you don't need to worry about this part. It's going to be taken care of for you. What you need to implement is this part. So again, the flow is you implement this part. This is the update amount, and the optimizer controller code is going to call a step function. And what this does is it applies the gradient step in that update direction. So let's look at the actual example. So simplest thing is SGD, which we covered in the class. And we need to do this update, right? Theta times that t plus 1 is theta t minus learning rate gradient of the loss with respect to the parameter. So now we derive from the optimizer base class. And this is just some helper function. So if you call model.graddict, it computes the gradient, and using the gradient, if you execute WD gradient here, this adds the gradient contribution from the regularizer. Okay, so these two lines gives you the gradient of the whole thing, including the regularizer. And this is what we need to provide as output, which is this portion here, right? Because if you look at the step function, it subtracts the step dict, which is output of the update dict. So parameter takes itself, subtracts this portion. So this is this corresponds to eta times the gradient of the loss. That's what this updated is supposed to output. Okay. Maybe it's helpful for you to see the actual call signature. Okay, so we're going to create a transformer model and load in some data set and push some token string and label, and the model outputs the logits and the loss. And we're going to call the backward that we implemented together. And from the optimizer class, we're going to execute dot step. Okay. This is the call signature. So grad logits is initialized to 0 from outside, and DL loss gradient of the loss with respect to itself is initialized to 1. And once we call the backward on the model, we're gonna call optimizer.step, and we're gonna repeat this process. This portion not necessary. That's the call signature, and let's implement this part. This is the easiest example today. While you're implementing, so I don't know if we will have time to cover SSMs, or state space models. So it's kind of similar to RNNs that we talked about in the class. So RNN, if you remember, condenses every single information in a single latent vector. So pros, memory no longer blows up. Cons, we do not have explicit access to the features of the past tokens. So very active research area. How can we enlarge this token length? So I don't know. I'm just shooting straight out of blue. So transformer or some architecture will have, I don't know, 10 years of knowledge explicitly referenceable. Right now, it supports up to 150K tokens. So what is the research that's needed in order for the model to have explicit access to every single tokens for, I don't know, 10 years of knowledge? And I think this is not just algorithm question. You also need to think about the computer systems and how to store different memory into different portions. Maybe longer context needs to get stored in the disk, and shorter context based on some algorithmic prioritization need to get stored in the memory, and etc. And how do you efficiently kick out unnecessary KB caches in the process as well? All done? All right. So it was just one line, right? I already gave you the answer. It's eta times the gradient, right? Next up is momentum. So SGE is very susceptible to local minima, as you can see. If you ever run into a portion where gradient is near zero, then you're never going to move. You're stuck there. So the idea in momentum is don't use the gradient as it is. Now we're going to do update based on what's called velocity or momentum. So momentum is some weighted averaging of the past gradients. So it's beta, which is set to 0.9 or 0.99 or 0.999 times its past velocity plus the immediate update amount. So we are very pessimistic in incorporating the current estimated gradient. So think about a ball rolling down on a mountain hill, and if it passes through a very narrow trough, then even though the gradient is temporarily flat at like zero, it's just going to keep rolling down. And that's why they named it momentum. So let's implement this. So here we created a temporary tensor initialized to all zeros. And this is same as before. This just gives you the gradient, including the regularizer component. And you're supposed to implement this part. So this is already given to you, right? And so the update, so in terms of our code structure, this is the expected output, right? Because when we call the step function, we're going to subtract from the current weight whatever is on this side. So the update dict function should output this guy here. So regarding the extreme long context research, Professor Jaeok Lee and Gun-hee Kim and Jaeung Shim in EE and Sang-woo Mo in Postec and we formed a team and proposed a government research program last month, and we heard our team was selected among 10 teams, and we are going to be supported about $10 million for 5 years. Very good news for us. And we said we'll create an extreme long context model that can support like 10 years of memory. I don't know how, but we have to make it work. Okay, so very easy, right? So let's look at it. So it's beta times previous velocity plus eta times plus the immediate gradient. So initially this is all zeros, and it's beta times itself plus learning rate times the gradient. And we're going to return the momentum dict, this part. Okay, RMS prop. We're going to look at the equations more carefully in the lecture in about 3-4 lectures. So idea is now we're going to keep around this thing called G. So this is some accumulation of the path gradient. So we still have this beta term for momentum-like behavior. And here, we're going to take ln(y)'s square of the loss. And then take the square root and add some epsilon. So the idea is following. So this is a vector of the parameters. So if you think about the updated equation, it constitutes of many different dimensions. Some dimensions, the gradient is going to be very small. Some dimensions, the gradient magnitude is going to be very large. So we want to provide some form of normalization. If the gradient there is very, very large, the magnitude is very large, we want to divide it by its gradient magnitude, or some running average of the gradient magnitude. This is ln(y)'s division as well. So the update is not so big. And if the gradient magnitude is very small, since we're dividing by it, we're going to amplify its update amount. So the update amount is now somewhat normalized based on the gradient magnitude, or to be exact, history of the gradient magnitude. That's what's happening inside. Does it make sense? This is ln(y)'s division and ln(y) square. So large dimensions get attenuated. Dimensions with large gradient magnitude, small gradient magnitude gets amplified. All right? So good intuition to have in your head is something like this. So let's think about a 2D optimization where we have very asymmetric loss landscape. So in one direction, the update amount is very large. And to be precise, in vertical dimension, update amount is going to be very small. In horizontal direction, update dimension is going to be very, very large. So let's say we are initialized here. It's going to take forever to go down this path vertically. If we are initialized here, convergence is going to be very quick. Right? So, I don't know, if we initialize here, the gradient component here is very small compared to the gradient component here. Okay, to make it symmetric, let's do it this way. So if we do this form of normalization, then we somehow morph the loss landscape, so dimensions with small gradient magnitude gets amplified, and vice versa. So something like this happens in Newton update. In Newton step, you you multiply by the inverse Hessian, and that's what happens here. You normalize the update dimensions. Okay, so unfortunately the time is up, so we're almost done in lecture 9. So it's just going to be a couple more lines, but we'll pick it up from next lecture. Thanks.